or B delta if you want, times delta. So this in X plus B delta square, and something else. And the reason why having something else here, as I explained, is because when you have delta of X square, and the reason why we have to have something else here, as I explained, is because when you go, when you calculate delta of X in Fourier space, you have something like delta square of K, which means that these guys strongly depend on the cutoff you have, because this is equal to delta of Dirac K minus P12, delta of P1, delta of P2, which means that if you take two modes, P1 and P2, which are in the UV, so let's say those are UV modes, they can sum to give you something like an IR mode K. So this means that either you trust what you have here down to very small scales, or you have to add a cutoff here, lambda, to regularize those fields, such that delta square here now depends on lambda. And then it means that you have something here that depends on lambda, here that depends on lambda. So this guy is linear, it doesn't matter, but you can say it depends on lambda too. And you have to promote the bias parameters here to also depend on lambda. And this brings us, okay, you also still want this guy to be independent on lambda. So you can ask, if this guy depends on lambda, is my basis complete such that if I go from lambda to lambda prime, I have a basis that basically rotates. So, okay, generically I can write it down as a sum O, BO of lambda, O of lambda. If I just take delta and delta square as my set O, is it complete, or do I have to include other kind of operators to regularize this theory? And the answer is, as we saw, we fixed the renormalization scheme to be the following. So how to define something? So the idea is that we wanted something here that doesn't necessarily depend on lambda. So we want to subtract something here. Oh, let me erase this part here. So we wanted to define some bias parameters that do not depend on lambda, but are renormalized such that I take my O lambda and I subtract some counter terms that depend on lambda that exactly cancel out the lambda dependence here. So what do we call here? So the way to define this is the renormalized operator, which we wrote as O, with these two brackets, two square brackets, such that this guy here doesn't depend on lambda, but this guy, okay, if you promote the bias operators to depend on lambda, you allow the bias parameters to depend on lambda, but the idea is to define something here that do not depend on the arbitrary choice of lambda that you put, such that the bias do not also depend on lambda. And the intuition to define, how to define what's this guy, what's this guy, how to define them. The intuition is the following. We define a B delta square, so this is the linear bias square, to be the limit when K goes to 0 of the two-point function. So the idea is to use the two-point function to define the linear bias. And similarly, we can do the same and define something like B delta square. So this is B delta renormalized square. So how to define something like B delta square, similarly to what we have done here, the renormalized B delta square. The intuition is that we can take the limit of the bispectrum of the galaxies, matter, for instance, and divide by bispectrum of matter, in some configurations of K's going to 0. That's the intuition. Use the three-point function here to define a second-order bias parameters.
I'll have to subtract delta
B delta cubic. So this is GMM. And the rough idea is that you can always go to a tree-level calculation such that, oh, yeah, of course. So the idea is to have some bias parameters that do not depend on lambda. And to have something that do not depend on lambda, we want something here that do not include loops. So this is an IR limit. Or you can always go to the IR limit such that the loops, the lambda dependence cancel out. So here what you have is a tree-level diagram, right? So you have something like a linear calculation. So this is linear. So basically all the loops that you have here and here cancel out when you go, when you take k going to 0. Similarly here, you can go to the bispectrum for B delta square. So I'm going to write this diagram here, which is delta square. So this is k minus p, and this is p. And you can contract this with two linear legs, such that I go to the bispectrum and I only have tree-level calculations here. So the way to define this is via tree-level calculation, and this also you can use a tree-level calculation, such that there are no loops, and you can say that this is lambda independent, such that this is lambda independent. So I'm yeah, but B delta you already fixed here, right? So you already fixed this parameter here. Yeah, exactly. So you fix the B delta using the 2-point function, and you fix B delta square using the 3-point function. So hello? Sorry? Okay. Right, so then I'm going to write some expressions to explain mathematically what I meant by this. So here what we do to define something that's this renormalized operator. So O is something like O of lambda minus counter terms that depend on lambda, such that if I take the contraction of this renormalized O with linear legs, so it means I take the contraction of this, so this is evaluated at P1, at P, and I evaluate something like with linear legs. This, I just substitute this value here, and I get something like O of lambda delta 1 plus O of lambda delta 1, sorry, counter terms, delta 1. And I split this contribution in two contributions, one that's a tree-level contribution and one that's a lambda-dependent contribution. So this is equal to O of lambda delta 1, tree-level plus O of lambda delta 1, that has some loops and is lambda-dependent plus some counter terms that depend on lambda, delta 1. And then I enforce that the loop calculations here are exactly canceled out by these terms, such that I define my renormalized operator to be equal. So the tree-level contribution is exactly equal to this, and those two terms cancel out with each other. So my renormalization condition is basically that the operator evaluated at some loops cross-correlated with linear legs exactly cancels out. I'm adding counter terms such that I exactly cancel out the loop contributions of my operator evaluated at loops. So, okay, this expression looks complicated, but the idea is that everything that comes with loops here, such that those guys, for instance, is canceled out by counter terms. So I want to take delta square, for instance. the first thing I can do is to cancel out the one lag contribution. So there is one loop contribution, that's this one, that I have to subtract in order to renormalize delta square. So I say that my renormalized delta square is equal, delta square, is equal to delta square that depends on lambda minus something like this diagram that if you calculate is just sigma square of lambda. So if you want to cancel out the first one lag contribution, no linear lags here, you have to subtract this term, which is just the variance of the linear density field. So if you calculate this, is just the variance of the linear density field. Yeah. Yeah, exactly. Yes, exactly. So this is what I'm going to show now. So this is when I contract with 0 lags here. So if I just take n here to be 0 and take the expectation value of my operator, which is the expectation value of delta square, I get something like sigma. Okay? But then I can take n equals 1. And the diagram I get is something like this. And then you can check that I just subtract this contribution here. Okay, just this is something different. Okay. To cancel out this contribution here, I have to add. Okay, I have the one that was the one coming from here, but I also have to add something that's a number times delta. So when I impose this renormalization condition, it tells me that to cancel out the lambda dependence from this kind of operator, I just calculate this kind of diagram. It tells me that I have to add something that depends on delta here. And then I go to the next condition, which is n equals 2. So this is, this type of diagram. And also this type of diagram. So I can either contract with 2 different legs or contract in the same leg. And imposing this condition with n equals 2, imposing with 2 linear legs here, which means going to higher order in terms of operators, it means that I have to add something here that's proportional to delta square of lambda. So to renormalize delta square, I have to add delta square at the next order, basically. And if this was the whole story, we would be very happy to have this basis here, including just delta and delta square. But this is not true. What happens is that when we do this calculation for n equals 2, we see that we also have to include something here that's proportional to del I, del j of phi, del I, del j of phi. So this is the trace of this tensor, right? So this is basically taking this, tracing, and taking the square. But I have to include something else here, which is something more, something beyond delta square. And this something beyond is the traceless, like basically the part that's not in the trace. So this means that this basis here that we included before with delta and delta square is no longer enough, and we have to include something else, which we call the Galilean operator at second order. And the Galilean operator is basically something proportional to the non-diagonal part of the trace. First order, we are fine, because you don't have, it's linear. You don't have this kind of thing summing to give you UV divergence. If you go to the next order, you're going to have third order operators here, which means to regularize delta square, of course, these is subleading contributions, but you also have to add some third order operators. And then you can play this game, like for whichever operators you have. Yeah. Yeah. Exactly, but then this is exactly what we expected before from GLR, right? Because this object here all combinations from this building block that's del I, del j of phi are exactly what we expected from GR. Plus the other ones that I mentioned before, which are del I, del j of phi v, the velocity potential. Those are the only two types of operators that we expect to be there by GR. Yeah, of course, like all combinations, also contractions, all possible contractions of them. Okay? Okay, so this was the story I presented yesterday, and the idea here is to live in a world in which we don't care about the dependence on lambda of the bias parameters. Here, by doing this, we are assuming a scheme in which we cancel out the lambda dependence. But what I wanted to do now is to understand the lambda dependence here is to construct something which is the renormalization group for the bias parameters. So what I want to do is to actually understand how those bias parameters depend on lambda. So different than what we did here, which is to cancel out the lambda dependence, imposing a renormalization scheme, what I want to do is to understand the bias dependence on lambda, because eventually this can lead to resummation of some terms. Okay? Yeah, in principle, the dependence on how you choose the filters that you put here, how you introduce the lambdas here, should be absorbed by counter terms. Everything that's basically, that lives on lambda, which is way larger than the k-modes you're interested in, should be canceled out by counter terms. Okay? So this was the work I developed together with Fabian Schmidt, and also Karl Lempus-Nicolis contributed to generalize this work to include primordial non-Gaussianities. And the way to proceed and to understand, the goal is to understand each one of the bias parameters dependence on lambda. So this is the main goal. How can we get a BO of lambda? Because this tells us that if we move from lambda to lambda prime, this tells us how the bias parameters change. And eventually, this can lead to extra information. As I mentioned, like in the context of particle physics, we know it brings more information due to some resummation of higher loops. Right? So the goal now is just to understand this. The focus on which kind of information it brings is something that we are trying to develop now and to understand further. But the goal now is to understand this bias parameters dependence on lambda. And yeah. Exactly.
So this lambda is the cutoff, right?
This lambda is the cutoff.
And then you're going to integrate over a shell like
Perfect. So the way to proceed, as Rogerio mentioned, is to do Wilson-Polchinski scheme. The idea is that when you move, what's the Gaussian initial conditions that we have? We have a Gaussian initial condition for the galaxy for the matter density field delta 1. When you move it in a lambda and you move this cutoff to be lambda prime, how does it change the bias parameters? So this is the question we are trying to address. So what happens when I go from one lambda to another lambda, which is basically a lambda plus a shell, a small shell, which has width small lambda, and we take this small lambda and bring to 0. When you take this small lambda and bring to 0, you basically get a differential equation for this BO of lambda. What happens when I integrate out modes that live in this shell? So this is the question we're trying to address here. What happens if I take a small shell, a very thin shell, and integrate out? So the goal here is to first come up with something that operates in the field level such that we don't have to go to correlation functions as we are doing here, because going to this kind of structure of correlation functions is quite nasty. So we have to start with something that gives us the correlation functions in terms of the Gaussian field. So the Gaussian field that we have is delta 1 for matter. So those are the initial conditions. So I want to integrate, I want to construct something like a path integral over my Gaussian initial conditions. And I want to construct a partition function z that generates me the correlators, basically. So to do this, I just plug my z with a current j, and these delta 1s here that I'm integrating over have some probability, some Gaussian probability. This p of 1 is just a number, so this is basically just a function which is the Gaussian measurement. I'm just writing p of delta 1, so this is the free action integral. And to get the correlation functions, what I do is to plug inside this partition function something like this j here coupled with my delta g.
So in field theory, this P would be exponential I.
Exactly.
The action.
Yeah, the I can absorb here in the j. I mean, I'm just calling my...
But in this case, you don't have a Lagrangian formulation for this.
Exactly. So I don't have a Lagrangian formulation, so I'm not plugging. So this is very important, that here, this j over delta g, j times delta g, this is nonlinear. This, what I get here, is the solutions of the equations of motion. So what I'm doing is taking the solutions of the equations of motions and plugging directly coupled to j. It's different than what we normally do in QFT, in which we have a free term here, j independent term, in which we integrate over the Gaussian measurement, plus including some interactions here. And we generate basically the solution perturbatively. What I'm doing here is to directly couple to the current my delta g.
Delta G depends on delta 1.
Perfect.
You don't know this dependence.
Yeah, I know this dependence.
You know this.
Yeah, delta g of delta 1 is equal to b delta of lambda, that depends on delta 1 of lambda, right? Plus will be delta square of lambda, that also depends on delta 1 of lambda, and I know this dependence, plus bg2, g2, that also depends on delta 1 of lambda. And I know this was what we talked about last time. We understand how delta depends on delta 1. So this, to understand this dependence, I'm using EFT for matter. Okay? I'm using the equations of motion, Euler and continuity equation to get this. I understand this dependence, so this is a functional dependence, of course. But this is something I have, okay? Such that if I want to calculate, for instance, the 2-point function of delta G, I just have to take derivatives of my partition function with respect to J and take J equals to 0. Or generically, if I want to calculate endpoint functions, I just take n derivatives of my partition function. Is it clear? Because when I take derivatives here, the delta G drops, and this is what I get. Okay? Just to explain what I mean by this, this is J of x, delta G of x, integrated over x. Or in Fourier space, if you want, this is an integral of J of k minus k. Okay? Something important here is that this J is chosen to have some support on lambda, such that whenever I calculate my 2-point function or 3-point function or n-point functions for case way smaller than lambda, this J support is chosen such that I'm allowed to do it, okay? J here has to have some support on lambda. So it just means that after lambda, if you go to wavelength, like wave modes that are larger than lambda, this J here is going to be 0. Okay? I'm just having had a hard cut on J here. Questions? So the way to proceed now is the following. I have constructed this partition function, and by the way, this was the work, this partition function was the work of Cabas plus Schmidt. So now that I have my partition function as a function of the initial conditions, the initial Gaussian conditions, I'm going to move from lambda to lambda prime and integrate out the thin shell. So this is what, as Rogero mentioned, this is what's called the Wilson approach, for which Polchinski generalized to construct this via this path integral formulation. So now I want to go from lambda to lambda prime. So I can take my z of lambda prime of j to be the integral of two different things, delta 1 of lambda times this shell. I'm splitting my integral in two parts, one that lives in lambda and the other one that lives in the shell. And then here I have E of j of lambda prime delta g of delta 1 of lambda prime. Okay? I'm just splitting this part here. So I'm going to write this delta 1 of lambda prime as something like delta 1 of lambda plus delta 1 of shell. So this now is a double dependence. And I'm going to explain what I mean by this. So for instance, when I take any operator that lives here, so this, as I said, is a sum of BO times O of delta 1 of lambda, delta 1 of lambda shell. So when I take, for instance, delta square, it just means that I'm taking my delta square that I had before, and I'm splitting this into two different contributions. So this delta square has many legs coming out here, many linear legs that I have here. Okay? This, okay, to explain what I mean by this diagram, maybe it's time to explore the diagrammatic notation here. And what I mean is, this is just the convolution of delta square. So delta square is equal to P1, P2, so what I have here is delta of P1 and delta of P2. And for each one of those legs here, I'm expanding each one of those delta here's onto different linear densities. So this one I can expand as a sum of delta n, and this one as well as a sum of delta n1, delta n2. And each one of them has an f and kernel, right? So basically what I'm writing here is generically expanding these deltas here in terms of deltas, in terms of f kernels here. And then, as I said, the idea is to take the operators here that before lived in delta lambda and to also consider delta lambda and delta shell. So each one of the delta ones that I had here before, I'm going to take as this plus something like a UV contribution. So it's basically the lambda contribution plus the shell contribution. Okay? It's just a diagram. Questions? I'm just taking, so basically I'm saying that delta 1 that I had before, delta 1 of lambda prime is equal to delta 1 of lambda plus delta 1 of shell. So each one of the delta 1s that I had before in lambda prime, I'm splitting into a shell and a lambda contribution. Okay? Oh yeah, sorry. I'm gonna be very sloppy here. P delta 1. Yeah. Yeah.
So you're splitting the integral there. What you're doing, you have to split the
Exactly. I'm splitting into.
shell.
Exactly.
And then some of the fields will be outside the shell, some of the fields will be inside.
Perfect. Perfect. That's it. Some of the fields here internally will have shell contributions. I will have all sums basically of shell cross lambda, shell lambda cross shell, all the possible contractions here.
So the integrals are in the exponent.
Yeah, the integrals are here. Okay? Is it clear? More or less, why?
Operationally, it's not very clear, but yeah, I just don't understand this last comment that you said. I mean, delta G, now you also have the byte expansion for the shell, like you also have delta G of the shell, which is exactly the same, but substituting.
So the operator that before was defined in lambda prime, so this is defined in lambda prime. This contains the sum of some shell modes with lambda modes. This is basically the sum of all possible like splits between shells. Each one of the legs here that was before, the sum of those two is equal to lambda prime. So you take each one of the modes that lived before in lambda prime and you split into a lambda and a shell contribution.
Okay, I thought the shell was like literally a shell between lambda and lambda prime.
Yeah, that's true. I'm taking delta 1s here. So this would be before delta 1 of lambda prime. And I'm splitting delta 1 of lambda prime to be delta 1 of shell plus delta 1 of lambda. Yeah. Yeah. I'm choosing basically, yeah, yeah. Yeah. And calling one, I'm taking one single degree of freedom and calling it 2 different degrees of freedom by choosing some support. Yeah. I'm choosing the modes. I'm taking one field and calling it 2 different fields that live in 2 different momenta, which are orthogonal, right? Okay? It's important that they are orthogonal, such that the contraction of shells and lambdas do not leave, like if you take the contraction of them, it's 0. Okay? Orthogonal means that if I integrate over k of delta 1 of lambda and delta 1 of shell, this is 0.
So you have like non-Gaussianity. That's in this case showing that the modes are independent in k-space. We have that modes are no longer independent in k-space, which might be from non-Gaussian conditions. Is that already down?
So everything here is Gaussian. This measurement here before was Gaussian because I'm taking the free theory here, and this is Gaussian. Delta 1 is Gaussian. And I'm integrating over the initial conditions of the universe, for which in this case are Gaussian. Delta shell is also Gaussian. Okay? Okay. Yeah, I know in terms of digesting those things, it's very heavy in terms of notation too. So, I mean, if you can grasp the big picture, it's the idea here. So, right, so then what I'm gonna do is take this exponent there and expand, because I can say that my shell is infinitely thin. So the fact that my shell is infinitely thin means I can take this exponential and decompose in 2 parts, one that's lambda and one that's the shell part. And at least the shell part I can expand in the exponent, right? Right, so I'm gonna expand this part here, each one of the operators here, O, I can decompose them to be some part that leave. So let's take my O in lambda prime and decompose this in terms of the number of shells they have. It just means the number of shells. I'm taking my O and basically counting how many shells does it have here. That's the count, the power count I'm doing. And then I'm gonna take the counting and expand in terms of the number of shells that I have. Because if I take this and expand, I'm gonna have something like this, right? Z of J of lambda prime. You need two shells. You need two shells. Because you're going to take contractions of them. I'm going to integrate over the shells here. And what's going to remain is basically the two shell term. Because when you integrate, so the idea is that I want to perform this integral here. I want to perform this integral analytically. And the integral of a field that has a single shell, it's a Gaussian integral. So everything that's Gaussian and has one single shell is going to give me 0. And the only thing that's going to remain is this O2 with two shells. So when I take this integral over the shells, I'm taking the contraction of two shells here. I'm just telling, okay, so if I want to perform this integral, it means taking contractions of those shells here. Taking the expectation value with respect to the shell, right? So it means contraction shells here. If I take an operator that has one single shell, this is going to give me 0. If I take operators that have two shells, it's going to give me something, which is what I want. 3 shells, again, going to give me 0. And 4 shells is going to be suppressed by loops. If I take 2 shells, contracted, it's going to give me something that's suppressed. 4 shell construction, sorry. I'm not sure if, is it?
Yeah, but because I think you have a whole interactive field there. Forget it.
Okay, so I'm going to forget about the probability, like just the measurement of the linear density. I mean, just for notation here. So it's going to give me something like J of lambda prime delta G of delta 1 lambda. So this is basically this guy that has 0 shells, the one that lives in lambda. And I'm going to expand the exponential in terms of the number of shells. So this is going to give me 1 plus the contraction. I'm taking the exponent here. So the contraction of J, O, I'm going to sum over O, of course. Of B O's in terms of number of shells, so I have to sum over the number of shells. So I'm taking this exponent here and expanding because I can say that shells are very thin, which means the width of those shells are very thin, so I can expand in terms of the number of shells. So I'm just summing over the number of shells and also summing over the operators that I have of O to the power of n, with n shells here, okay? So the dots here are basically O's order, sorry, not the same O's as this. Order, let me write order J square terms. I'm going to talk about these terms later, but what appears here is something that's order J square. So higher order in the current terms. I'm going to explain these terms later, but let's focus on these terms now. Yeah. Yeah. So I'm just splitting the which coefficients you mean? Because you mean different bias coefficients?
No, I just mean that like delta shell nonlinear is some sum of delta shell linear. Those are the nonlinear ones.
Yeah, those are the nonlinear ones. And shells means I'm taking nonlinear number of shells. I mean, this is nonlinear. Okay, this is a complex structure. I'm just writing down very schematically here, but this is a general operator like expansion in terms of shells and lambda modes. Okay? So it means that now, when I take the expectation value with respect to the shells, it means taking the contraction here. So everything that's here goes as here as some contractions for the shells. Okay? I'm just taking the integral here and saying that this is the expectation value of this operator with respect to the shell integrals, the shell integral measurement, okay? And in the end of the day, it means that I'm taking these O's, for instance, for delta square, and I'm generically taking everything here that has one shell contraction, either like this, or like this. Okay? There are two possible shell contractions I can take. So if I take one single shell contraction, it's 0 because the initial condition is Gaussian. So for n equals 1. So for n equals 0, it's basically this term that I had here before. For n equals 1, it's going to give me 0 because it's Gaussian. For n equals 2, those are the possible guys that I have. For n equals 3, it's again 0. For n equals 4, it's basically the same kind of diagrams, but with extra loops, which are again suppressed. They're suppressed because they're higher loop contributions. They're going to contribute with lambda. Basically, they're the two loop guys, like these ones. They're proportional to lambda to the fourth. Lambda being the width of this shell, which means when I take lambda to 0, they're going to die sooner as these kind of diagrams. Okay? Cool. So those are the two types of diagrams that I have. So those are the two types of diagrams that I have to compute. And then it means that my z of j at lambda prime is equal to d delta 1 of lambda p of delta 1 e j lambda prime delta g of lambda 1 plus some corrections with two shells. Let's say O2 yeah, sorry. Okay? Then this is the part I have to look at the notes. So this basically allows me to go and calculate, I'm going to call this object here. Okay, so let me write this expression in a cleaner way. So it's going to be j of lambda prime. So this is the bias at lambda prime times the operator evaluated at lambda, plus some SO2. And SO2 is the two shell contractions. I'm calling S because it's a shell contraction. I'm calling it a 2 because it's a contraction of two shells of an operator O. And this depends only on lambda. Now everything here only depends on lambda. Okay? Right, so this gives me something that's the following. So this means that if I take my j, you see that j here is the only thing that has a lambda prime more than the bias parameters that also have a lambda prime. But if I take the support of j to be in lambda, if I'm focused on correlation functions that are evaluated for k way smaller than lambda, which is of course same order as lambda prime, I don't care if my current is at lambda prime or if my current is in lambda. This should give me the same result. This should give me exactly the same result because k is way more than lambda and lambda prime. So this has to be equal to z of j of lambda. Make sense? Because both partition functions should give me exactly the same result. Doesn't matter if I choose my current support here to be lambda or lambda prime because the support of the current here that multiplies, like that has a narrow part that lives in lambda prime is going to give me 0. So it means that I can remove the lambda prime here. And this should be equal to z of j of lambda prime, as long as I restrict myself to these conditions. I'm interested in correlation functions for k modes that are way smaller than lambda and lambda prime. And this is equal to delta 1, p of delta 1, j of lambda, sum over O of BO, O of lambda 1, of delta of lambda 1. So I can compare both expressions, this with this one. And then I get the following. Then it means that the sum of BO lambda O of delta 1 of lambda, the sum over O, has to be equal to BO of lambda prime plus the sum is over everything. Sum over O prime of some numbers which I'm going to call small s, O, O prime, BO of lambda prime, O of O prime. Sorry. So this just comes from comparing both expressions. So this S here is just one number, which is the number I get from evaluating this shell. So this is just an expectation value over the shell. So this is one number. So basically one coefficient. So it just means that my BO at lambda is basically the sum of BO at lambda prime plus lambda, small lambda, the size of the shell, times the sum over B O prime. So here I'm summing over O prime. So this is the contribution of the operator O prime to the operator O. So what it means is that I'm summing over all the operators O prime, and I'm asking how much this operator O prime contributes to O when I move from lambda to lambda prime. Okay? And something really nice that comes out is that actually those coefficients here that we get, so this S O primes that we have here are basically a coefficients C, O, O prime, times something that's D sigma square D lambda evaluated at lambda. So it just means that how much the increment that I have from going from lambda to lambda prime is basically proportional to the variance of the linear density field at lambda prime. So my differential equation that I can draw from this is actually very simple, and it means that D lambda, BO lambda, when I take lambda, so from going here to here, I take lambda and bring to 0. It just means that the derivative of my operator at lambda is just minus D sigma square lambda, D lambda, times the sum of some coefficients, C, O, O prime, B, O prime at lambda. So this is the final expression that we can have that describes how an operator O prime, which I'm summing over here, contributes to the running of an operator O. It's here, it's here. So I already integrated out the shells, right? So I'm already summing over the O prime. So here's the contribution of. I already integrated out. So this is the expectation value of O prime I took here.
So you're assuming that the O prime is just assume the expectation value of O prime?
Yeah, I calculated the expectation value of O prime, and it enters only via these coefficients, those numbers S here. So the expectation value of O prime gives me some numbers.
Let me ask another question. If the bases were complete,
Yeah.
S would be 0, or B 0.
Exactly, exactly. If you find the basis to be complete, some lines of this S is a matrix, right? This S is a matrix. So some lines or some columns of this matrix would be 0 if the basis was complete. Okay? Okay, long story short, I mean, you can use this expression here and calculate this S. I can show some examples for this S, but it's very lengthy. I don't think it's the point. But the whole point is that from moving from lambda to lambda prime, again, I basically can take lambda to 0 and calculate the contribution of the operators O prime to some operators O, and this is proportional to D sigma D lambda. So the fact that this depends on D sigma D lambda tells me that as bigger as my variance here, so here's the PDF of delta, so it tells me that as bigger the variance is on a scale lambda, more my fields will contribute to the operator O prime, O here. Okay, so basically if I move from lambda to lambda prime, I gain an increment from the operator O prime that tells me how the bias parameters change here. And then I can solve for these ODEs. And this set of operators I can have in a table. Okay? Yeah. Yeah. Exactly. So these S's here that I calculated here, which are the expectation values of O's, they're going to basically add. So this contains a sum over all possible O prime operators that contribute to O. Okay? So these enters, I'm summing over O prime, which are the different all possible, for instance. Okay, just to give some example here. Maybe it's good to give some example and to write down the expressions explicitly for some of the bias parameters. So to calculate the example here, I'm going to calculate how delta square contributes to other kind of operators. So when I take delta square, which is the one I wrote down there, and I calculate S delta square 2, so the shell contribution, the true shell contraction of delta square, it gives me something like 68/21 delta plus 8126. Again, you probably saw those magical numbers before. So surprisingly, it's exactly the same magical numbers you had before, times integral of p square dp 2 pi square p shell of p. P shell of p is just the linear power spectrum calculated in a very small shell. So it means that the contribution from delta square to other operators, so delta square, when I take the shell expectation value of delta square, it's going to generate a contribution to delta, it's going to generate a contribution to delta square, and it's going to generate a contribution to G2. When I take these two shell contractions here, it appears very nicely that what I get is exactly the same I had before, the same coefficients, but it turns out that it has some slightly different implications. But what I get is exactly the same coefficients I had before for the other renormalization scheme, but now it's quite clear that it generates a delta square, it generates a G2 when I take this shell expectation value. So it just, okay, so then if so those are basically the C coefficients I wrote there. The C, O primes that I wrote there in the other part of the board. So then if I write down the expression for D, B delta, D lambda, it's equal to minus 68/21. So it gains a contribution from delta. It also gains a contribution from delta cubic. And it also gains a contribution from so this factor here is exactly this factor here. You can show that this is basically the variance of the shell, and this is the variance of the shell. Okay. You can also have an expression for B delta square, D lambda, which is equal to minus. So as you see, the number that we see here for B delta, the contribution from B delta square, sorry, here is the B delta square. The contribution that we get here is exactly the number that we got here. So this is due to the fact that delta square generates a delta. So delta square, as you move from lambda to lambda prime, delta square is going to source a delta. So this is the meaning of this expression. Right, so I think I can move now to show some slides and to flash the results of these equations. The idea is to measure this in simulation. So this is something we're aiming to do now, to measure those bias of the evolution with lambda. Yeah. You take the simulation, you measure something for one lambda, and then you move the simulation in a different lambda prime. And you calculate the bias, and then you smooth in a different lambda prime, you calculate the bias again, and this is the, yeah. Yeah. Why? If so you generate, so the idea is that you generate some bias parameters, you take a simulation, you run the simulation, and you measure something like for one fixed lambda. You take, this is not the simulation smoothing exactly, but you take the simulation and you smooth again over a scale lambda, and you measure the bias parameters. Well, for instance, using some, you can take B1, you can measure easily on the large scales, and for B2, you can measure, for instance, in the, taking the large scale limit of the bias spectrum. Yeah. Exactly, exactly. Totally agree. You measure this with endpoint functions. You measure with endpoint functions, and then you compare it to what I expect here. Yeah. Yeah, exactly. So you just take a simulation. I'm gonna show some slides, and I think this is gonna. So you take something like a simulation, and you measure the bias parameters, for instance, using endpoint functions, and then you move the simulation in a different scale, and you measure again those bias parameters. Yeah, just the, I mean, it's just the same box getting smaller, but it's just like to say I'm smoothing the, and then it gets smaller and smaller. Yeah, yeah. No, it just has to be smaller than the simulation because the simulation has some resolution, and it has to be larger than k to ensure that you have those conditions. So it has to be some smooth. For instance, if you're interested in modes that are 0.1, you just have to do a smoothing around 0.2 or 0.3 or something. Yeah. You can also do that, but also you can take the simulation and smooth. It's basically the same, right? Because then you're measuring directly. I mean, if you can measure directly if you can construct the fields directly from the operators, and you measure the bias associated to each one of those operators, it's basically the same. Taking the final simulation, smoothing the simulation, and measuring each one of the bias parameters is exactly the same as taking the endpoint functions, and those two things are exactly the same. Right, so the idea is then you take, for instance, a box, is to understand how this simulation, for instance, change as you zoom in or zoom out. And as I said, the equations you want to derive is something similar to this current semantic equation, which is dg d lambda, which is the scale as you evolve in scale. And this, on the right-hand side, you gain something which is the beta function of your theory, which tells you, in the case of QED, the beta function for the electron charge here and the electron mass, if you want, is something like proportional to the E cubic here. For the QCD, for the gauge coupling, it's B of G, something like this, proportional to G cubic as well. And then you do the same for the bias parameters. You have the bias expansion, and you want to understand how changing the simulation as a function of scale affect the evolution of the bias parameters you measure. Mm-hmm.
You measure the galaxy power spectrum in the simulation,
No, no, you cannot apply it to the power spectrum directly. You have to apply it to the operators, right? So you have a simulation and you have, so you want to PGG is equal, for instance, to B1 square, P matter, plus B1, let's say B1, B delta square, P matter, let's say delta square, right? And then, but this is different, right? I'm not taking the direct PGG and doing a cut. I'm taking the operators here. So P m delta square of lambda is different than P m delta square lambda prime. I'm doing this move in delta square because this is delta square of lambda and this is delta square of lambda prime. Yeah. You can do that at field level, for instance. You take a field, you compute delta square. For a simulation, you know the initial conditions, you know delta, the final matter, for instance. You find halos. Let's take halos because it's easier. You calculate delta square for this simulation, and you can calculate the coefficient that's in front of here, right? Exactly. This guy cannot depend on lambda. So what you're doing is moving the fields directly here. The basis you choose to fit those parameters is different. Okay? It's not that you're taking this and doing like just a cut. Of course, this is.
But the n-body simulation has the full nonlinear, like has infinite nonlinearity, right?
Yeah.
Why do you assume that truncating the operators in an n-body simulation gives you the same behavior as truncating the EFT calculation?
Because you also have in the EFT part, like everything should be captured also by the counter terms. You also have some extra counter terms. And at least for the matter part, the counter terms that you have here, which are like delta k square, they should absorb this part. At least when you restrict yourself to large scales, the counter terms should absorb this part for dark matter at least. Okay?
How large is this? Because then can you go back to what the last lecture, which is the gauge issue. So it's not really the very large scale, but it's some.
So here, I'm thinking about case around 0.1 compared to lambda. The lambda you take, like, for instance, in a simulation, you cannot go beyond something like 0.7, right, 0.8. Probably you can if you do like a lot of effort, like with barons, even harder, right? But if you do something like K1, I think it's, so with simulations, you can always have something like lambda 1 or something like this. So there is a hierarchy between this and this. And then you do this move in here in two different scales, for instance, 1 and 0.9, and you measure how much the bias change as a function of lambda. Okay? Right, so the idea is that the comparison between the two renormalization schemes that the one in which you remove the lambdas, if you read Polchinski's original paper, he says, originally renormalization was just a mean to removing infinities from perturbative calculations. So removing lambda dependence or removing infinities is just something that, if you want what you observe to do not depend on lambda, you remove those infinities, right? But also taking the cutoff seriously and allowing the operators to change with lambda and understanding how they change with lambda is something that can add an extra piece of information. So that's why we did this shell expansion. So you see that, okay, so what is in yellow here, what's in orange, is basically the corrections that you get. So SO1 would be, can I use the pointer? I'm not sure. So SO1 is what you get from one shell correction, which is 0. SO2 is the contribution that I was calculating here. But you also have something which is these higher in J terms that appear here, that I didn't mention. So these higher in J terms, when you take derivatives with respect to J, those terms are going to appear as some extra stochastic corrections. Everything that has higher powers in J is going to appear as some stochasticity. So J square terms are going to source stochasticity for the power spectrum. J cubic terms are going to appear as well when you do this expansion. And they're going to source stochasticity for the bispectrum. And this way, you can basically calculate corrections to stochasticity as well. So as I said, the one loop term here is important. So what you see here is the one loop term. And when you go to stochasticity, it's actually the same. But the one loop term looks a bit more complicated. But it's still like this. The one loop terms that you see here are exactly what source stochasticity for source corrections to stochasticity. Yeah.
How are they suppressed with respect to this? How do you see the suppression?
Good point. So I'm gonna come to this in the slides. So if you look at the equations that you gain in the end, so this is what I was just flashing there in these equations. What you gain here on the right-hand side is something like an integral of P shell, which gives you d sigma d lambda, which tells you that the width of the linear density is what basically controls how fast the bias parameters will evolve in this RG flow. So these S coefficients here, or C coefficients in this notation here, are basically just numbers you can put in a table. So you put those numbers in a table and you find that which parameters here source which type of operators there. And then you have some equations. And as Rogério pointed out, the equations, for instance, for delta, they involve B delta square. The equations for delta cube, and they involve also delta cubic here. And also, so you see that the running of delta, which is a linear operator, a first order operator, has operators on the right-hand side which are second order and third order, as those two here. The running of operators that are second order, as those two here, have operators that are second order, as those. Operators that are third order, but they also have operators that are fourth order. So one question that appears is how to truncate this hierarchy of equations, because always, if I want to solve operators that are first order, I need operators that are third order. If I want the operators of second order, I need operators that are fourth order.
The language of field theory, this is a non-renormalizable theory, in the sense that there are an infinite number of counterterms. Order by order generate more and more counterterms.
I'm not sure, because here you can actually show that you can, so it's always suppressed by this parameter here, d sigma, d lambda. So it's actually coupled. It's indeed true that it's coupled, but what we have discussed also in the paper, I don't have the plots here, but what we have discussed is that you don't need to understand, you don't need to solve the full set of equations to get the running of these terms here. Just because the running of the fourth order operators, take here these equations for instance, the running of B, for instance, fourth order is not relevant for BG2. So you can take this guy here to be just one number, one fixed number, which is a constant. So we're putting a star to claim it's just a constant in one fixed value. So you can just fit one number here in one fixed value of lambda. You don't have to consider the running of all the terms together. In principle, you would have to consider the whole tower. To get a full analytic solution, yeah, you would. So this is something we've been thinking about, if we have fixed points beyond the Gaussian fixed point. If you put all parameters to 0, then the right-hand side is 0. Yeah. So this is a fixed point, but this is the trivial fixed point. But what you see here is that if you start in a cutoff lambda with some value of the bias parameters, basically your bias parameters will evolve towards different values. And also what's funny is that see that B1, which is in red here, can go from positive here in this lambda towards negative values here. So it can even change sign. Also BG2, which you calculated. It makes, it's a void. It's a void, right? In a different lambda here. And what you see is that BG2, which was 0 here in this cutoff, is also sourced. So it means that you have to include BG2, because if you just change lambda and BG2 was not initially there, it's going to be sourced. And then you can draw this kind of, schemes in which you run the bias parameters together and think about the RG flow together.
The bias parameters, they have a very clear physical meaning, right?
Yeah.
They are, you can measure them almost independent, like in large scale, you can measure them independently of
Yeah.
damping, right?
Perfect. So
So it's not that they can change, like,
the bias parameters have a very clear physical meaning in the large scales, as you said. And what we show also, this is something we have derived, it's 10 pages of derivation that we had, is that when you take lambda and bring to 0, which means it's exactly like this renormalization scheme that we mentioned. You take basically the loop contributions and suppress the loops when you take lambda and bring to 0. The value you get here, basically this cut in this plot, you see that it goes to a constant here. And the value they get here is exactly the physical meaning you were mentioning. This is the intuition that you have, like this is the large scale bias parameters that you measure using, for instance, separate universe. Yeah.
It's running on lambda, what it's indicating somehow is what terms are more relevant. I mean, the thing is that because I understand that when you look at very large scales, you have a physical meaning.
Yeah.
Now that you have the running with lambda, it's somehow telling you something about what's relevant at different scales.
Exactly.
Parameters.
Exactly.
But it's not that clear what it's now that you are pushing to smaller scale for lambda. No? Like what
What's the meaning of
that? Yeah.
how to interpret a bias value here? It's just the bias measurement you would make if you take the operators here and smooth and scale lambda. Take a simulation, take the operators, construct these operators on top of a simulation with a cutoff lambda, and measure those bias. So in a simulation, normally in a simulation, like with an intrinsic cutoff lambda, which is large, you don't measure the large scale bias parameters, right? You measure this in a fixed lambda. Unless you do this trick that you measure like them using the endpoint functions, taking some limits of k going to 0, what you're going to measure intrinsically is something that's lambda dependent. Because the operators are there for one fixed lambda. You're smoothing the operators as well, right?
Initial conditions are taken at large lambda, and then you're running to low lambda.
Yeah, here what we're doing is fixing lambda to be 0.2, and then we are running towards smaller lambdas. And you see that there is a connection between lambda and sigma square. So sigma square is here. So you see that basically the parameters change as large sigma square is. So here sigma square is quite small, which means they don't change much. Okay. Right, so as I said, we also consider primordial non-Gaussianities. And what's quite nice is that you now have an equation not only for B delta. So you see that B delta before was just something like this term that we had before. So this blue part. But now when you include PNGs, you also have something like this orange part here. So it means that you can also have the running of the B's depending on FNL. So you see for two different values of FNL. So I think it's something like 10 and 100, something like this. So the two different lines mean what happens if you turn FNL on. And they also induce some running in the bias. So here are basically the same, but for the non-Gaussian bias parameters. So you see B phi and B phi delta, which is the second order non-Gaussian parameter, and how they change for two different values of FNL. So you see that you can also see the evolution of the FNL parameters. And this is a very nice derivation of this Neo-Dalaus result from 2007, because what you get here is exactly this 1 over k square that you have for the bias, for the B phi. We also do for the non-local ones. This one is for the local one. So, what do you mean? Sorry, defective? Oh, we just initialized them here. So we initialized them here in one fixed lambda, and we analyze what happened for two different values of f and l. So we initialize them in the same value, and we want to understand what happens when you run towards smaller lambda.
So is fully predictable? Like if I measure using EFT, the bias is at 1 there?
Yeah,
I
it's
predict exactly how much they are in the large scale.
yeah, you can. So if you know one point here, you can predict all the points. And if you're not able to do it, it means there is something else missing. Either some higher loop contributions that are missing in your theory that you forgot to include. So this is something very predictive, means like you expect the points to run exactly as the lines are here. And if it's not happening, something is missing. Either you are in a regime in which the two loop contribution is relevant, or you are in a regime in which perturbation theory breaks down. So
So in terms of what Francisco asked before, that you can measure bias response, when you're doing this, right, you have to do some kind of averaging. So this would mean that you can then look at the bias one scale, and you can predict what that's going to be on any average scale.
yeah, that's true.
The problem with the prescription that you mentioned before is that you need to do some force gradient of zero,
Yeah.
you cannot measure this, let's say,
Yeah.
or whatever bias.
Yeah.
But if you measure in one scale, then you can in principle predict what's going to be in the different.
Yeah, that's 100% true. So what we provide is some differential equations. So we don't provide initial conditions. So if you measure something like in the initial slice, and if you want your initial slice to be, for instance, separate universe value for the bias, if you measure the separate universe value for the bias, you can predict those bias for all lambda values. Yeah. Well, so I think they're careful enough to do it in these slides here. So putting priors are still fine, because as long as you put priors on one fixed lambda and you know the lambda you're putting priors on, it should be fine. I don't think it screws anything. It's I'm not saying anything about the initial values here and the values you're putting priors on top on. What I'm claiming is we provide an unambiguous way to know the lambda you're putting prior on. Like we're fixing, basically, this question brings like, okay, you should be careful about the lambda you're putting priors, but as long as you do it, it should be fine. So as I mentioned, something that's sourced by this, if you just start with this ansatz here that we have for the partition function, and you expand, you're gonna generate naturally some higher in J powers here, which contribute as stochasticity for the power spectrum, for the bispectrum. And what you can do is, again, to derive equations for these stochasticity terms. So P epsilon 1, epsilon just accounts for stochasticity. This is the shot noise. This is the normal shot noise that you have. And you can also derive the running of the shot noise term, as you see here in the bottom.
So stochasticity comes from the short wavelengths that are not observed.
Yeah.
Two short wavelengths.
Exactly. Two short wavelength contributing generates something like P epsilon 1, right? So the contraction of epsilon epsilon is something that generates this operator.
And this comes from shells that are...
So this comes from basically initial conditions, not the shells only, but like everything that's basically in the UV that generates like a constant flat term that we know that can source a constant flat contribution. So this is the flat shot noise contribution. Okay. And what we see is that delta square, as we saw yesterday, like if you take the limit like of the kernels, delta square has no kernel here. If you take the limit of k going to 0 or the limit of p going to infinity, there will be a constant term in delta square that you have to subtract. And this basically means you have to, delta square generates the running of the shot noise. Delta square also generates the running of the shot noise of the bispectrum. And you can see here the running. So it's really nice because suppose you want to do some analysis in which you don't have any stochasticity. If you just run from lambda to lambda prime, stochasticity is also generated. If you have delta square, you see here that delta square basically generates stochasticity to all orders. So delta square is the devil, like it's gonna generate stochasticity. And then there's a very simple diagrammatic picture for stochasticity as well. So this is those are the type of diagrams that generate stochasticity. Those here. So those ones here generate the bias running, but those ones here generate stochasticity. So this is what you have for the stochasticity running. So the running together of the stochasticity parameters together with delta square. So the reason why I think it's useful, and to conclude, I think it's useful for extra cross-checks of EFT inference, because as I mentioned, you can compare the prediction that you had for the running with what you see in simulations and see if there is anything missing. Also, it's a very systematic way to renormalize the bias and stochasticity parameters, also including primordial non-Gaussianities. Because if you try to do the other way around, the one in which you subtract infinities, you have to be very careful about what you're subtracting. Also very careful about the order you're calculating the things. Whereas here, it's everything for granted, so you just have the running, and it's basically, it's super simple. It's just the running with these ODEs that you have to solve. So you also mentioned the priors. It provides a very unambiguous way to define the priors for EFT analysis, which is when you take lambda and bring it to 0, because then you reproduce this large-scale bias limit. If it has more information, it's something we are trying to think about now. You can also connect this to other kind of fields, like in terms of condensed matter and other things, and think about phase space, think about phase transitions, also critical exponents. But this is something to be determined that we've been thinking about. So yeah. So the idea in the end is to wrap up, just to wrap up the lectures, is like cosmology is becoming something more like particle physics, more and more, in which we think about correlators, we think about EFTs, we think about this renormalization group story, and what we can gain from this. So precise data, I think now we are able to catch up with providing also precise theory. So this is the main message.
So, some more questions for yes.
So, when you, first one, very basic one from the beginning, when you put the V1 squared P matter matter, what is defined the linear bias with respect to the limit of your galaxy with respect to your matter matter? Why don't you do it with the matter galaxy?
Oh, you can do the same.
There's no.
No difference.
When you talk about the primordial non-Gaussianities, did you just like change the PDF for delta 1, or can you do it directly by looking at the variance and including the correction that you have?
So the way we include non-Gaussianities here is to change the measurement here. So non-Gaussianities are basically new type of vertices in your theory. So it means that, so here we only have one type of vertex here, which is basically those FNs here. But when you have PNG, so okay, so before, for instance, if you have contractions, you only have contractions of this type, right? So in the case of Gaussian issue conditions, you only have the power spectrum here, right? Contracting things. In the case of PNG, you have a new type of vertex, which is something like this, which is a B, the B's of the initial conditions. And this accounts for a new type of interaction that goes beyond the Gaussian interaction. So this means you have to modify this Gaussian measurement here. So the way we account for this is to add a J independent term here, int, which is some interaction, which is basically the bispectrum of the PNG, or the trispectrum of the PNG, if you want. So this means that every single, so for instance here, if I want to generate, so it means that, for instance, if before I had something like this, so this is the way, for instance, delta square would generate a delta. Now I have something else, which is something like, I don't know, Because here is a power spectrum, right? So I have also a bispectrum that can generate something else. So there is a lag here that comes from the bispectrum. We show diagrams like this in the paper, but this is the way you would, for instance, source a delta contribution. But this is proportional to FNL. Okay? So there's this new type of vertex that you have to include. Yeah. Yeah. So I don't think it's, well, good question. I would have to think about it and write down, but I don't think it's one specific configuration like the squeeze gives you B delta square. I think it's the sum of all possible configurations give you the sum of B delta square and BG2. But the shape, basically, they have a shape, right? So this allows you to fit B delta square and BG2 together in terms of degrees of freedom. See what I mean? No. Yeah. Yeah. Lunch?